Okay, so this is the last chapter of this whole course. Okay, and we'll talk about the dynamics of orographic pressure. Okay, let me see. I still have to upload the book chapter. Okay, yeah, so. But for now, I think the basics are here. And if you need more reading, you want to learn more, then you can read the book chapter, chapter 11. Okay, the organ influence on climatological distribution of pressure. Okay, the climatological distribution of pressure is significantly influenced by the mountains. Okay, for example, like this. Okay, if you look at in 1971 to 1990 over the Western Europe, and you look at the those no data is over the ocean, and you look at the high pressure places, a lot of them are associated with mountains. Okay, so this is the Western Europe topography. Okay, so almost controlled by the mountains. Okay, like here is Alps, and this is Pyrenees. Okay, and this is coastal mountain of Italy. Okay, this is Italy, right? And what's this area? Yeah. Adriatic Sea, okay? Yeah. It's here. Okay, and this is Croatia. Okay. Croatia and Slovenia also has part of these Alps. It's called Dynamic Alps. Okay, this is the main part of the Alps. Okay, second example is, the third example is Taiwan. Okay, so see, you have the highest precipitation controlled by over the high mountains. Okay, and the second example is over the South America. Over the South America here. Okay. And you can see also the rainfall controlled by the mountains here on the eastern side of the mountains. Okay, and what you have very large rainfall here. They are not related to mountains. What are the cause of those? My question is, you see, you look at highest. Of course, you have the mountain in influence orographic rain here and also here. Okay, and how about here? Those are huge rainfall. That's ITCG. Okay, that's Amazon. Okay, that's Amazon. The forest, rain forest. Okay, but besides that, you can see the rainfall are controlled by the mountains. But it's very interesting. You look at here. Okay, the heavy rainfall is on the western side of the Andes, and here is on the eastern side of the Andes. And the reason is because this is in the easterlies. So the rainfall are on the eastern side of the mountain, and here is on the westerlies, in the westerlies. So the heavy rainfall is focused on the western side of the mountain. Okay, so that's very different. Do you see a difference compared to Taiwan's and compared to Alps? See here, in Alps, the maximum rainfall is over the mountain peak. Okay, and Taiwan's too. Okay, see, maximum rainfall. We're talking about climatological rainfall. Okay, we're not talking about 1 day or 2 days or typhoon comes in. We're talking about overall for long term, the being averaged rainfall. And here, okay, the reason is because for small mountains, for small hills, okay, the flow comes in, or a kind of passive system comes in, and this here maybe make it simple. The flow comes in, moisture flow comes in, and it's going to be lifted, okay, and then you have to lift up to the, okay, LCL, and then to get things going to form cloud, and you want to have convective cloud. You have to lift up to, if it is conditioned unstable flow, you have to lift up to LFC, okay, and all those, and then you have to get the microphysical processes, okay, going, kind of get going, trigger them to have interactions. So if this is small here, okay, and the flow comes in, okay, and it starts to have the rainfall process, but it's already passed over the mountain peak. So, okay, and sometimes to the lee side. So, for small hills, the rainfall maximum is over the mountain peak or downstream, because it takes time to, okay, form the rain, okay, and then for larger mountain, okay, like Taiwan's, okay, and the Appalachians, okay, the kind of Alps, okay, it's also like that, okay, and you have small peaks, okay, in there are many small peaks, so it's over the mountain area, okay. But if it is a low, it is a large mountain, then, okay, when a flow come in, lift it, has enough time to make rainfall and focus on upslope. So it depends on the scale of the mountain. It's not the maximum rainfall always on the mountain peak. It's not necessary. Okay. Oh, sorry. Okay, so figure even point A to A. That's this one. Okay, that's over the South America, reveals the annual rainfall distribution over the Andes. Andes is the very low mountain range, okay, along the western side of the continent. And in South America, has the rainfall maximum located on the eastern slope in the northern Andes. And in southern Andes, the heavy rainfall is focused, okay, on the western slope. Okay, and I explained that already, okay, because it's westerly, and in northern Andes it's easterly. Okay, and 11.2b indicate rainfall was produced mainly from the lifting and blocking of the prevailing wind, okay, from the southwesterly monsoon flow and multiplied by the mesoscale convective system, mainly front. Okay, so Taiwan's rainfall has, you are very familiar with, okay, we mainly produced by, okay, northeasterly monsoon during the winter, and then during the May season by the May front, and then typhoon season, it can come from anywhere, but mainly from east, okay, but even from east, because of circulation, okay, you have the heavy rainfall here, but the outer circulation would come all the way, and then kind of put rainfall here. But this is not only by typhoons, because you have southwesterly monsoon coming in, like in May and June, okay, and even July, you have a lot of rainfall here too, okay. And nothing to do with May front, okay, you have rainfall here, okay. And so, but overall, after average is still the rainfall maximum located over the mountain peak. Okay, the maximum rainfall over a snow here is often located over the mountain peak or downwind slope. Okay, it's because it just doesn't have enough time to form the rain. Okay, normally it probably take about 30 minutes to form the rain. So if the here scale is so too small, then it's going to pass it, okay, quickly, okay. But of course, you're going to get drifting and then get things going, but then some of them will dump the rain on that downslope. Okay, so this shows the example. Also, not only the rainfall distribution is not only related to the mountain scale, it's also related to the basic wind, okay, the speed, okay, and also direction. Like here gives the direction, okay. You have different direction, you have different rainfall distribution. Okay, so see here, this is Rapid City, okay, and this block here, okay, and so here we got two maximum rainfall, okay, and so from different directions you have different rainfall distribution. So that's kind of trivial. I think you can understand that easily. Okay, the intensity, duration, and distribution of orographic precipitation are mainly determined by the following factors. Okay, these are very important factors, pointed out in 1956 by Sawyer. And he said, first, the large-scale environment, which determines the characteristics of the airflow, okay, upstream of the mountain. And second one is dynamics of the air motion over and around the mountain. Okay, depend on two-dimensional or three-dimensional, also depend on the floor number. Okay, how strong your basic wind coming in, how high is your mountain, how stable is your flow, and so which determines the location and layer of orographic clouds and precipitation. And another thing is the cloud microphysics processes. So larger environment. Secondary is lifting, blocking, okay, mechanical forcing. Okay. Third thing is microphysical processes, okay, and which is very complicated already. And then when impinge on the mountain, it's getting even more complicated. Okay, and not only that, because those three are not totally separated. Okay, because, for example, this air motion going over the mountain, the lifting, that's mechanical forcing, but that can trigger the thermal forcing, and that trigger the microphysical processes. Okay, and that microphysical process can even feed back into the mechanical forcing. Okay, for example, if this is just simple, but there are many examples. Okay, so you have upward motion, and then you start to form the rain coming down, and then below the cloud base, there will be evaporation because you are in a region which air is not saturated. Okay, so then it's going to evaporate, and then you're going to have the cooling, and cooling will form denser fluid, and then will push. Okay, I guess the flow can be this way, okay, and that will form the density current, okay, and in front of it is, okay, gas front. So you can kind of feed it back and then provide additional forcing, okay. Okay, second thing I wanted to discuss is the orographic modification of pre-existing disturbances. Okay. The most significant impact of the orography, the mountain, okay, on the rainfall is not by trigger the rainfall distribution, trigger the rainfall by itself. It is by enhancing. Okay, that means, okay, normally strong rainfall is not when you have the moisture flow impinge on it. It is when you associate with like cold front, okay, like tropical cyclones, like extratropical cyclones. Okay, so that's most important thing. It's pointed out by Smith 2006. He said mountains usually multiply and often amplify rather than create precipitation. Okay, and create precipitation is just like when you have the flow, there's no weather system, and then it just comes down and then created, produced by mountain. That type of local rain, normally it's still very important, but compared to when you have a system like a typhoon, you have a hurricane, they impinge on the mountains. Okay, then that compared to that, it's relatively insignificant. Okay, I would say like insignificant because sometimes we have like very moist, okay, monsoon flow, okay, coming in, it still, okay, produce heavy rainfall. But relatively speaking, the enhancement multiplied, okay, the rainfall investment associated with the weather system impinge on the mountain, okay, that is relatively small. Okay, a prevailing wind or pre-existing weather system like typhoons, hurricanes, okay, or extratropical cyclones or front, they can influence the orography by one, providing larger scale upstream conditions such as wind speed and direction, humidity, stability. Okay, like if you have the prevailing wind or the flow embedded in the pre-existing system, and if they are kind of conditionally unstable, okay, then when you impinge on a mountain, okay, it's going to be triggered, because trigger means you have strong lifting, and that can go up to force the air up to the LFC. Okay, then you release the instability, and then everything kind of goes, because you blow up, because you got strong upward motion exerting upward. Okay, and then trigger the microphysical processes and dump a lot of rain. And second thing is can generate additional forcing through dynamical processes due to its interaction with topography. Okay, so like when you have a typhoon, okay, here's east, right? So the typhoon comes in. It's not only the basic flow impinge on the mountain, because typhoon you have the okay, the very strong wind, okay, around the eye wall, and that eye wall, that strong flow impinge on mountain, the part is especially strong, okay, especially compared to the basic flow impinge on the mountain. Okay. Let me see. I have it in my computer, otherwise I can show you. Yeah, I have it in my computer. Okay, anyway, so I probably can bring my computer here in next lecture. Okay, so also affecting the microphysical processes in orographic cloud formation by providing the characteristics of hydrometeors and stability, okay, and through its interaction with topography. Okay, so next thing I wanted to talk about is, so you ask yourself, there are so many heavy rainfall which a lot of them can lead to flooding. So what are the common synoptic mesoscale environments? Okay. In order to understand the basic dynamics, we have to kind of collect all those information from different events. heavy rainfall events produced by mountains or enhanced by mountains. Okay, and then come up a conceptual model. Okay, so what are they? Okay, so based on like there are several studies, well-known studies. Okay, of course there are many of them, and they are very complicated. One of them is like a mid and upper tropospheric shortwave trough, like in the States, okay, the America. Okay, they have several very famous historic events which produced flooding. Okay, and then they found, okay, many of them have a trough approaching the mountain. So like I have mountain area here. Okay, and normally you have a trough, mid or upper level trough, like approaching it, the mountain. Okay, that's very common, and that also happened for the rainfall associated with flow passing over the Alps. Okay, and the American mountains, and which is propagating toward a high pressure ridge axis. Okay, high pressure ridge axis. So normally you probably have a synaptic situation which you have a ridge like this. Okay, and by some reason this one is not moving altogether. This one can move faster, maybe like associated with a front. Okay, and this one can move toward this ridge. I'm talking about not mountain ridge. I'm talking about the synaptic, okay, ridge, high pressure ridge. And so they observe this, and then second one, like here. Okay, this is maybe let's look at this. Okay, that's easier. So this is this conceptual model, okay, schematic of the synaptic and mesoscale conditions conducive to heavy auricular rainfall is derived by 4 major events in America, okay, in the States. Okay, that one is 1972 Rapid City flooding, and South Dakota's flood, 1977 Big Thompson Canyon, and then Colorado flood, and then 1997 Fort Collins. Okay, Fort Collins is a city, the CSU, Colorado State University, located. Okay, and okay, also 1995 Madison County, Virginia flood. So those, based on those 4 big events, and they come up with the conceptual model. So here you have okay, so here okay, so you have a kind of pressure ridge here. See here, pressure ridge. Okay, like I draw here, the pressure ridge. So your pressure ridge is here. Okay, 2, 3. Okay, the pressure ridge. Okay, and then there's a okay, where the trough can impinge on this ridge, and normally also associated with surface ground. And also importantly, you have a low-level jet here, low-level jet. Okay, because high pressure, and then that bring the air from east, and that okay has the low-level jet, very strong flow, impinge on the mountain. Why do you need low-level jet, by the way? Why do you need a low-level jet? Okay, because if there's strong flow impinge on the mountain, compared to weak one, low boundary condition. Right? Low boundary condition. Remember, that's why we needed to learn the basic mountain words. Okay, like low boundary condition. So flow like this, you have ear. Okay, so this low bound condition will have okay, W equals to E plus H plus X. Okay, the mountain slope is fixed for a particular mountain. Okay, so if strong, if this is very strong, this will be very strong. Okay, and that's part of the reason you need, okay, strong low level jet. And also conditionally unstable flow, because if you have condition unstable flow, and if you have a way to lift, force this low level flow up to LCL, you start to have the cloud forming, but not enough. You have to force further to the LFC, the level of free convection. Okay, and that's the one of the conditions. Okay, it drives everything crazy because you have strong acceleration. Because you release the instability, you convert the convective available potential energy into kinetic energy. Okay. So it's shooting up, and that the convective clouds, okay, form after that. Okay, so all those, and also you need a very high theta E, that's equivalent to potential temperature. Okay, that's normally require you to be very moist, and also very moist. Okay, flow. Okay, and warm. Okay, flow. It's not only that it's when you have low level flow, which is theta E is very high. That means, okay, this jet has very high theta E. Your theta E here will be smaller than this. Then you could have potential instability. Okay. So you could have potential instability, and on top of that, you could also have the potential instability if you have a large cap. Okay, now we go to the arcs. Okay, I always use arcs and as an example is because I'm very familiar with. Also, it's a very famous place for cyclogenesis as well as heavy rainfall for arcing. Okay, over the arcs. But also because I kind of participated in the mesoscale alpine program, okay, for about 10, 12 years, so I'm familiar with that. And also I use the example of Taiwan, okay. It's kind of almost free advertisement, okay. Maybe Taiwanese government has to pay me something, okay. In my book, I have so many examples of Taiwan's everything, okay. Yeah. It's also because I'm from here, right? Yeah, I'm familiar with that. Okay. Yeah. I don't know what people think, okay. Okay, if you like it, you can write a book, okay, and then you issue your country's phenomena, for example. Nobody will complain. Okay, anyway, so here, very complicated. Normally, you also have a, like this arcs, right? So, this arc. And normally, you have different kind of situation, of course, but one major situation is you have a trough coming in, and this trough also associated with kind of front, cold front, okay, because your mean altitude, okay, the other things are dominated by front. And then at low level, you have low level jet here, okay, and east of the side, you're easterly low level jet, and these are alpine mountains. Okay. Okay. And then you also have this is French Alps, okay, and this is Apennines, okay, Apennines. This is Italy, okay, this is Italy, and this is Mediterranean Sea, and to the south it's Atlas Mountains. Where's Atlas Mountains, by the way? Where's Atlas Mountains? That's Africa. That's northern Africa. Okay, this is northern Africa. Okay, and this is Pizonha. Okay, Mediterranean Sea, and then you have this trough has high PV. Okay, high PV, and this is trough. Okay, So things are complicated, okay, and that makes it kind of difficult to understand, okay. So you have to kind of tear apart and then study it. Okay, other phenomena is showing importance of LMJ, that is low-level jet. Like in this case, this happened along the California coast, okay, California coast, okay. So you have here's the coastal range, okay. Inland you have bigger mountain range, that's Sierra Nevada, okay. And then you have a very strong low-level jet impinged on the mountain here, and this is very moist, very moist, okay. And this is also low-level jet, okay, impinged on the mountains, like over there. And this low-level jet, very moist flow, it's kind of actually it's kind of a airstream, kind of being spin off from the ATCG, okay, from the kind of from tropics, and that is they call atmosphere river. Okay. They call it atmosphere river because it's kind of like a flow confined and then flow, okay, toward, okay, the California coast. Okay, sometimes it goes to the north, but California coast is the one being impinged a lot. And it's called river because it's very moist, okay, and flow in a very confined, okay, kind of, it's kind of spin off from the IPCG. So we have moist, warm, and low-level jet in the mountain, okay, and that can cause flooding. Okay, the prefrontal low-level jet is narrow, very narrow, warm, and almost moist neutral. Okay, which is very effective in transporting the water vapor toward the California, and it is called the atmosphere river. Okay. Okay, orograph learn associated with passage of a tropical depression over mountains in Kyushu Island. You wonder why I started this case? This case kind of brought my kind of attention. This is in this is associated in 1974. Okay, heavy rainfall in this island, okay, and this place is called the Kyushu Island, okay, and the mountain is not very high, and the system is not very strong, right? Because we have plenty of typhoons, okay. We have plenty of typhoons much stronger than this because it's just barely okay, tropical depression. Right? It's not even a tropical storm. Okay. So, but of course, strong flooding, that caught my attention. Why? Okay. Why? You ask question. Because if you wanted to have a strong rainfall produced or enhanced, you wanted to have a strong system, like a strong hurricane, okay, impinge on the mountain. Okay. But it's weak. Why? Okay. So that kind of bring my kind of attention, okay, curiosity. Okay, so and later we're going to find it. Okay, it's okay. That one of the reasons. Okay, it has because of the strong depression. Okay, it's kind of tropical depression. So you have a lot of moisture, right? A lot of moisture. It's warm too, but you also have low-level jet. Not very strong, but at least better than normal flow. Okay, and the thing is, this guy going very slowly. Okay, and that is also one of the factors. Okay, very important. Okay, this is just like a kind of a system. like weather system, for example, like a tropical cyclone, and come into here, okay, and then come over her house. I'd like to stay here longer. Okay, okay. So go slowly, and extreme case is just come on top of your house, and then don't move, and keep dumping the rain. Even this is a weak system. Okay, if you keep dumping rain, you're going to get a flood. Okay. Yeah, like a partition. And there are two partitions. Okay. One is on 1959, and there's another one probably 50 years later. Okay. Okay, and okay, so this is Taiwan's case, okay, which I probably don't have to spend much time. Okay, so okay, the time Taiwan comes in. I think this is a famous case in 1999. Okay, this also partition side. Second one. The first one is very famous because at that time Taiwan was kind of poor, so a lot of overseas kind of Chinese, they kind of donate a lot of money. Okay, so eventually they have money left over, so they built up 3 elementary schools. Okay, one is in my hometown. It's called 乔德国小，乔德小学。And later occupation goes here. Okay, so and other one is this August 7th, 1999. Okay, and both are associated with other stronger typhoon. Okay, in both two cases. Okay. So, and that produces heavy rainfall. Okay, so now, so just a quick recap of what we reviewed, those historical events. Looks like if I lift up, it's better, right? Yeah, maybe I should do this. Okay, yeah, this, I feel kind of the sound is, okay, kind of better this way, right? Maybe because it's closer. Maybe I bite it. Maybe I should bite it. Okay, so make it bigger. Maybe closer. Where is closer? Here? This is probably better, right? This is better. Okay. So, so what are the common ingredients of those? Okay, we try to find because, okay, we need steep mountain. There's no doubt. Okay, if it's kind of not very flat, okay, of course, it's not going to produce heavy rainfall. So you need a steep mountain, and we also found, based on those American cases, Japan case, Taiwan case, okay, European case, then we found we also need low-level jet, and this low-level jet has high equivalent potential temperature. That means it's moist, okay, and it is okay, high moist flow and high cap, okay. A lot of cases with high cap, and then quasi-stationary synaptic system, okay. You kind of come in and then decide, okay, oh, I don't want to go anymore, I'm tired, okay, so just sit there or very slowly moving, and that will dump a lot of rain in same place. Okay, so now those are what we found, those factors. And so those common features may be explained by you take a common ingredient approach, okay, approach. So now you just look at a simple way. You just say if we wanted to find how much rainfall being produced by a system in a place, okay, So you have a system here, okay, rainfall coming down like this. Okay, so total precipitation, it's pretty easy, right? Because total precipitation will be simply equals to rainfall rate, because this is in, say for example, in millimeter. So this will be millimeter per hour, for example. Okay, of course you can measure different way. You can measure like meter per second, whatever. But this is normally what we measure, and then times duration. Okay, so this is say hour. Then that give you total rainfall. Okay, that's no secret. Okay, pretty simple. Okay, so rainfall rate. Okay, times duration. Okay, so what is this and what's this? Okay, so first thing we want to find out the rainfall. Okay, rate. Rainfall rate will be equals to basically will be the W times Q. Okay, QV. Okay, what's W? W is vertical motion. Okay, and what's QV? That's moist. Okay, the moisture. Okay, you can measure it different ways. Like you can measure it by relative humidity, or you can measure it by the mixing ratio. Okay, or water content. Okay, so you can measure it. So why this is important? Okay, you wanted to get strong convection. You need a strong upward motion, and this upward motion can bring the moisture up. Okay, if this strong motion is here, okay, but you have high QV here, it's not going to help. But if you have high QV here, you have strong upward motion. That will give you the strong convective system. Okay, and so this is called the vertical moisture flux. Okay, and I don't know how many of you have heard of core scheme? How many? Core scheme, core scheme, KUO. No, 郭小人, yeah, 郭小人 scheme. Okay, he passed away. Okay, he was professor at Chicago. Okay, his Dr. Son's PhD advisor. Okay, core scheme was very famous. Okay, and it's very simple. Okay, and idea is like this. If because you don't have microphysics, so what he does is you detect the convergence. Okay, and this convergence is going to drive air up, and then you also detect the QV, okay, moisture, and then that's WQV, the press. If it's higher to a threshold, a certain value, then that's okay. You assume you have cloud, and that's core scheme, the cumulus parameterization. Okay, so different cumulus parameterizations have different bases. Okay, like Kent-Ridge scheme is based on Kep, not based on that. Okay, so core scheme is based on this vertical flux or moisture. Okay, and like pacemaker scheme is based on the how do you call it, the moist adjustment. Okay, so wherever you got kind of unstable moist flow in vertical, then you are going to have convection. And then he just simply, any kind of mixing, so he just simply bring back to the moist neutral. Okay, So, okay, so different have, different kind of chemistry parameterization have different kind of assumptions because they don't cloud. Their cloud are kind of virtual. Okay, you just calculate some terms. Okay, there's a cloud here. They don't really have the rain. Okay, to water vapor. They have water vapor, but they don't have rain. Where you have rain, those kind of processes, they don't. Okay, and so then that's proportion to this, and this also have to add into this rho divided by rho W. This is air density, this water density, because you are converting the air, okay, into the water. Okay, so that's why you need this one, and then you need a we call pressure efficiency, because when you have the moist flow flux based on vertical flux of the moist air up, there's no guarantee it's going to be 100% everything will dump, become rain. Okay, because some of them will dissipate or through turbulence, and some energy will be dissipated here, there. Okay, so that's okay. Have to add in. Okay, because not everything is going to become rain when you have the rainfall elements there. Okay, and so that's why we have this R equals to E times rho over rho W times WQV. Okay, and then next hour we'll start from here. Okay. Okay, so this is a conceptual model kind of sketch. I draw by myself. Actually, I draw by myself. Okay, I try to get my students, my kind of colleagues to do it. Eventually, I'm the one found it. Okay, how to draw it. So this is a talk I gave at at the last year's US-Taiwan workshop. Okay, and we have a group. We try to propose a field experiment in Taiwan. It's called PRECIP, P-R-E-C-I-P 2020. Okay. No guarantee, we are still writing it, and then we still need to be reviewed, to be approved, okay, to be granted. Okay, so by the way, okay, let me sidetrack a little bit. I found it very interesting. I found this by myself. Okay, it's record is there, but I found it by myself because I'm curious where has the world record for rainfall, because by a kind of misunderstanding in, I think it's 2009, right? That Morocco case, and by kind of probably misunderstanding, some reporters report in Addison there's a kind of world record break. Okay, 48 hours. So I check it. It's not. Okay, it's not. It's this small island, tiny island. Okay, and this is, which country is this? Madagascar. Okay, Madagascar is very interesting. Madagascar had a lot of kind of species. Okay, like plant and like animal species, which is very unique. You cannot find in other places in the world. Okay, and Madagascar was not originally stick with Africa, even it's so close to Africa. Okay, it comes from same place from southern hemisphere. Okay, go through the continental drift. Okay, 大气漂移论. Okay, come from with south. So then you have the South America. Okay, South America continent, and you have Africa, okay, and India. They originally are from southern hemisphere, and then they migrate long time ago. Okay, and then migrate, and then they split, and Madagascar split from India and South America. Okay, so it's very interesting because 2 years ago I had, or 3 years ago, I had a postdoc from Madagascar. You see, you look like me. She doesn't look like African. Okay, yeah, she said they have two types of people. Okay, the first immigrants, okay, is from from Asia, okay. That's they are those Hawaiian people, okay, those Polynesian, okay, how do you say it? Polynesian, okay, Polynesian, yeah, Polynesian. That they are Hawaiian, like Taiwanese, native Taiwanese, okay, okay, those people, and so they drifted to Africa, and then second wave of immigrants are Africans. Okay, yeah, so very interesting. Anyway, so there's a small island. It's called La Réunion. It is a French territory, not a colony. It's a territory. Okay, and so it's very tiny, and it's called La Réunion. Okay, and so you see here, 12 hour, 24 hour, 848, 78 to 96. Okay, this one is a championship. This small island. Okay, and only one is different. Is this one? Okay, this is no. This is Morocco. Okay, Morocco produced 1092 millimeter. Okay, still huge, but still okay, kind of weaker than okay, this rainfall compared to this 24-hour world record. And this is Indian case. Okay, that also have a like a wall. Okay, like a wall. Okay, it's a kind of okay. And besides that, all are okay produced here. Okay, and I was curious about why. Okay, so actually it is because of this term. Okay. I think the mountain probably not as high as Taiwan's. Okay. It's probably 2 kilometer or maybe lower 3 kilometer. And but mountain the island is so small, so it's very steep. Actually, myself have been there. Okay, I was invited to give a talk, actually a couple of talks in a workshop. Okay, I visited there. Okay, very very far away. Okay, and okay, so it's because of that partial H, partial X. Okay, so now I wanted to show you one figure which shows I sketched it. Okay, why in the environment when a typhoon, okay, or in general tropical cyclone passing over a mountain, why you had the environment. Okay, it's this Taiwan. Okay, and Taiwan's case also very interesting. Okay, you have this continuous track, and you can have a looping track. Okay, actually I probably can use this to deliver the lecture because it may be easier to see. Okay, so like this. This is the figure I want to show. So say this is Central Mountain Range. Okay. Or operations, okay, in America, or any other mountain range, okay, and this can be applied to the extra tropical cyclone too. Okay, so now you have a tropical cyclone, and the strongest wind, okay, is along the eye wall here. I will have strongest wind, and so when you approach it, this part will automatically provide the low-level jet. Okay, and that low-level jet is very strong, right? Okay, that is much stronger than the flow embedded that U. Okay, you normally have a kind of easterly wind. Okay. But that's much smaller. That is probably like 5 to 10 meters per second. And this one could be as high as 40, 50, okay, meters per second. or even higher. Okay, so when this kind of provide low-level jet, and also because typhoon is very moist, of course it's formed, migrated over the ocean. Okay, so you got high moist flow, and when you got steep mountain, you mean that island doesn't get world record. The island when it get world record is they have the tropical cyclone. They call it cyclone. Okay, tropical cyclone. Okay, passing through, not necessarily through. Okay, just passing by, and that provide same environment. You have high pressure. Okay, high moisture. Okay, you have low-level jet. So you have low-level jet. Okay, yeah, steep. Okay, and if it's slow moving, then you automatically get heavy rainfall. Okay, because you got all those ingredients or elements. Okay, produced by that. Okay, because this part is the eye wall, right? Eye wall you have very high moisture. Okay, so you got a lot of elements there, a lot of ingredients. Okay, so that's probably about it. And then the next thing is to apply to real cases. So I probably just stop here for this part. Okay, and then and of course there's some more things to develop. For example, let me go back to my PowerPoint. Okay, just briefly. Okay, I don't want to spend too much time on this. This is more advanced level. You are interested, you probably can go to the T-Fly, the Hontak Jungsim, next Tuesday. Okay, and yes, since across this, so let me make comments here too, because this is very interesting. This is related to what we've been studying. So one of my graduate students, right now he's working at the Argonne National Lab. Okay, he's from he's from that country. It's Turkey. He's from Turkey. So you see here, this is U1. That means 1 meter per second. 1 meter per second passing over mountain. 1 meter per second is dot of bracket here. You see dot of bracket. 10 meters per second, 20 meters per second. We're particularly interested in high wind. Okay, under the tropical cyclone environment. So you got 40 meters, 30 meters per second, 40 meters per second here. Okay, so you look at that. You have dot of great waves generated. Okay, hydraulic jump. Okay, dot of turbulence. When you get to 40, become quiet. Become quiet. You see, become quiet. Okay. So why? Say again. Evolution. Yeah, evolution flow. Very good. Okay. So this is we study. What we studied is just simple linear theory. And we study is very simple. We don't even have a rain drop. We just have the dry flow over mountain. And we found two major categories. Okay, one is great wave or vertically propagating wave. Vertically propagating wave going up. And then you have the evanescent flow. Okay, this is evanescent flow. Even for moisture, okay, and so we can apply actually in our paper 2017, actually this year's, okay. I tell him, okay, I wanted him to just apply the linear theory, okay, and then just make it moist flow, okay, the governing equations, very simple, okay, and then use that to explain, okay, you can have the flow transition from this low full number flow, that's braking, kind of medium full number, and then high full number flow, which you have evanescent fluid. Okay, so you have braking here, and then you have the vertically propagating wave. Okay, so you got hydraulic jump, but here you don't. Okay, it's kind of evanescent flow. So this is published in 2017, earlier this year, in JS. Okay, we also run in the large eddy simulation. Okay, and when you high speed flow, you get line up the convection. Okay, so other thing, I cannot stop talking about this paper, this slide. Okay, other thing we found very interesting is for high speed flow. Okay, for high speed flow, we have like 40 meters per second basic wind passing over mountain. That 40 meters per second, of course, representing the tangential flow of the vortex. Okay, and you see here, when you high cap, you produce like this. You draw cap, okay, you produce this. Oh, that's controversial. When we have this result, I was getting more, gray hair. Okay, yeah. I worry about grants. I worry about teaching. I worry about advice students. Okay, this is part of consulting. Okay, I worry about my daughters, and actually I have a daughter Joy. I don't have to worry. Okay, I had a Joy with my grandson. Okay, yeah. So this contribute to some of this. Okay, so why? Okay, why? Because you anticipate. You high cap, you got a lot of convective available potential energy to convert into exertion of the upward motion. Here you don't. You produce more rainfall. Okay, yeah. So this, you're interested. You can. Let me see. You probably can still download. Okay, so the formation and the enhancement of mechanisms of rainfall. Okay. So the formation and enhancement based on the dynamical and thermodynamic conditions of the upstream airflow, interactions between different layers of clouds, interactions between dynamical and the cloud microphysics processes, and mountain meteorology. Okay, mountain geometry. In the past, several major formation mechanisms have been proposed. Okay, one is the stable ascent. Okay, what is a stable ascent? That's the very kind of classical kind of mechanism proposed in elementary school textbooks. Okay, and like this one. Okay, this is normally what you see in elementary school. Okay. Textbook, okay, and that is kind of stable upgrade, okay, upgrade of the air, and then form the cloud over the upslope, okay, and so that's first one. Second one is release of moist instability. Then, in this case, you do have very strong vertical acceleration, okay, because of instability. So then the orographic clouds will be like this, Okay, so here instead of a kind of very smooth upglide of the air, here you got a strong updraft, and here one by one. Okay, here several, okay, updraft, very strong and very narrow, and then in between you have weaker, kind of compensated downdraft. Okay, so this is pretty common when you have heavy orographic rainfall. It's normally this type. Okay, strong updraft like this, and so that is the release of moist instabilities. No matter it is which kind of instability, you could have condition instability, could have the potential instability. Okay. And other one is the effects of mountain geometry, like here. Okay, so when you have a mountain, like isolated mountain, and then you have flow, kind of low flow, rumble flow, then it's going to go around, and then the split airstreams, they bump each other on this side, and then they can form the cloud and develop, okay, vertically. So this is, okay, the D cloud can form this way when you have the low flow, rumble flow, okay, split, and then they have convergence and produce upward draft. And other one is you have a combined thermal and mechanical forcing. Okay, mechanical forcing is you have forced updraft because of mountain. Okay, and then also in the meantime, okay, you have this updraft force is because you have heating here. Okay, so then you have kind of very wind go up, and then once very wind go up at the mountain peak, they meet, they have, okay, additional forcing because of convergence. Okay, so you have heating, and then you got this. So more or less like what we started in last lectures, like the mountain plains, okay, solenoidal circulation. Okay, remember that? Mountain plain solenoidal circulation. Like at night, you have kind of, we call it katabatic wind. Because it's cold, so coming down, but in the morning, okay, and then you start to have very wind going up, okay, and then eventually that will replace this part, and then they form, okay, this kind of orograph cloud. Okay, so that's number D mechanism. Those are only conceptual models. Of course, they are formed. Those are proposed based on observations as well as numerical simulations, idealized or real case simulations. Okay, so that's effects of that's D. D is combined thermal and orographic forcing. That's D. This is D, and this is orographic geometry. Okay, orographic geometry can have this type, but also can have this type. Like if you have a cloud, a mountain like this. Okay, and then your system. Okay, like for example, in Taiwan's case, like this. Okay, then we have the concave region. So you have southwestern monsoon coming in, and that can get the convection started here, or you have typhoons. And then the outer circulation that can put it in, and they start here, like in Gaoping, D3. Okay, here you have upward motion, and like in Alps, in Alps, when they have the trough moves in, and that bump into here, and there's a concave region, like the southwest concave region of Taiwan. This in Alps, okay. They have this. They also started from there too. There's a deck. It's called. This deck is called Dago, Mage-Ari, something like this. Okay. Spelling probably I forgot the spelling. Dago. Okay. Dago means deck in Italian. Okay. So then we have 4 types of, so mountain geometry can make the orographic clouds or pressure system develop differently at different locations, like develop on the this side, like this, will develop in the concave region. It's called concave. So, okay. Again, concave region. Okay, you can, because you have uplift. Not only that, you also have convergence. Okay, because flow comes into a concave region, it's going to convergence. Okay, besides you also have upward motion, so the uplift is stronger. Okay, other one is when you go out. Okay, maybe even here you hear people talking about. The cedar feeder cloud mechanism. Have you heard of it? Cedar feeder cloud mechanism. Okay, this cedar feeder cloud mechanism. This is kind of course, idealized. So what happened is this. Sometimes like. This kind of mechanism was proposed first by a Swedish, or it's by Bergeron, first by Bergeron, and also by British meteorologist, because in some area of Europe, except that those Alps, very high mountain. Some area they don't have very high mountain, just hills. And like England, only hills. Okay. So do you know what's the difference of hills and the mountains? Huh? Speak up. Yeah. Altitude. Their height. Yeah. So normally speaking, if it's below 1 kilometer, it's called here. It's above. Of course, it's not a kind of hard number. Okay, it's not hard number. It's just lower mountains we call hills, and high mountains called mountains. And like in England, they compared to Taiwan's mountains, nothing. Okay, it's nothing. It's all hills. Okay, all hills. And okay, so what is this shader filter mechanism? This is called shader cloud. Shader, shader cloud. Sheeting, cloud sheeting. Okay, this is just like a cloud sheeting, and this is filter cloud. Okay, filter cloud, shader cloud. Okay, so right down. Okay, shader cloud. Right. Okay, filter cloud. Okay, and so then in England, you don't have high mountains. Okay, but they produce a lot of rainfall. Okay, what happened is, they have this kind of mountain cloud, like that, okay, like that, like a T, kind of lower cloud. But they also, when the front passing through, there are 2 layers of cloud. One is by mountain lifting, they are kind of shallow cloud, not very strong deep convection. But then there's one deeper, and then at higher level, and that associated with the front passing through. And then this has the raindrop coming down, and then they can, like sheeting, they serve as the ice nuclei, as the rain, the cloud nuclei. Okay, how do you say it? 凝结核. Okay, 凝结核. And then, they already have the rain. Okay, so they accumulate more because of 凝结核. They serve that, and then, they develop, and then, produce heavier rainfall. Okay, this is just like similar mechanism, but not quite same. Like in the airport, sometimes they have fog. They have fog. 机场大雾. We have fog. And one way to eliminate them is, they just use the water gun, and then they spray it, because those, kind of small water droplets will serve as the nuclei. It's a kind of cloud nuclei, and then and then they kind of accumulate, and then they grow, and then they absorb those kind of fog, and then kind of dump down as rain, and then kind of cure the fog. Okay, so that one mechanism called the shader filter cloud mechanism. And like for example, Ron Smith has proposed this kind of mechanism is important when hurricanes passing through a Dominican island. Not the Dominican country, the Dominican island in Caribbean Sea, and he proposed that. So if somebody asks you, do you see this kind of shader filter mechanism in your simulation? One way to try to find it is trying to see if you have 2-layer clouds, and also if because your model, so the model can produce a lot of variables field for you. So you look at the vertical direction, and to see if your rain will have 2 kind of profiles, 2 layers. Here, rain here, and then here, or maybe ice. And then here we have kind of rain droplets kind of enhanced, in the lower layer. And then other mechanism is this is proposed by Smith and then House, and the mechanism here is, they say here when you have this kind of bumpy, okay, bumpy hills or mountains, then you got turbulence. So when a turbulence, then you have the rain and the snow kind of bump into each other, and then you got accretion, okay, process, and then kind of grow quicker, and then dump rain, okay, heavier. So that's another mechanism. So this mechanism is called the interaction of dynamical and thermodynamic processes, okay, and then you got turbulence going, okay. So that's what proposed. They are pretty easy to understand, okay, so just make sure you understand the key, okay, points. And other subject is the control parameters and the moist flow regimes, okay. So you may wonder what's a control parameter, okay. Remember, for dry flow over mountains, for dry flow over mountains, so say we're H here, and then we have A here, okay, half width, half of the mountain, and then we have U here, okay, we have N here. So we have U, we have N, we have H, we have A, okay. So we can form a number of the non-dimensional parameters. Okay, so what are they? You know, one. U over NH, and you have H over A. H over A is more or less like mountain slope. Okay, H over A, more or less mountain slope. And then, not exactly, okay, and then what's that? NA over U. Okay, just three. But those three are not independent. Only two, according to, okay, Buckingham pi theory. Okay, only two. So you can pick up this one and this one, or pick up this one and this one, or this one and this one. Okay, and this measures what? Make sure you understand this physical meaning. What's a measure of this? What's a measure of this? What's a measure of this? Nonlinearity. Nonlinearity. Okay. Okay. That the higher, the more linear. The lower, the more nonlinear. And what's this? You know this one. Okay. This is slope that controls the hydrostatic or not. Okay. I mean stronger the intensity of hydrostatic, and this one too. The larger of this one is more hydrostatic. Okay. The higher of this is less hydrostatic, more non-hydrostatic. So these two are non-hydrostatic measure. Okay, so then we know this. Those are control parameters. Okay, and you can pick up any two of them. It's control parameters for dry flow. Okay, so moist flow is similar. Okay, so basically you have dimensional parameters like U. And like now, instead of dry ground vessel frequency, now the difference is you replace this by N sub M. Okay, that's saturated, moist ground vessel frequency. Okay, and then. Okay, I have definition in the book chapter 7.3.12. Okay, by the way, somebody sent me an email to remind me I had to upload this chapter, book chapter, so you can read it. And then mountain height, right? Mountain height, just like we had here. And then, so only thing difference is we have this NM. And then you also have the earth rotation. Okay, so if we have a kind of larger mountain, we also have F. Okay, we have F. Okay, and of course you can have vertical wind shear. Okay, sometimes it's getting more complicated. You have to add more and more dimensional parameter, and then you produce more non-dimensional parameters. But then you have to check, okay, when you can propose any number of non-dimensional parameters you want, but make sure they are independent. And what's limit independence is by Buckingham pi theorem. Okay. Okay, so in order to thoroughly understand the complicated dynamics of orographic precipitation, the theoretical approach and or a systematic approach for performing idealized numerical simulations are required. Okay, ideally non-dimensional control parameters, if they are independent, okay, that will help us because you don't have to do hundreds of simulations. You can just use limit number of simulations and then you apply to real atmosphere because you have different kind of dimensional numbers, but you can only perform limit numbers much less than the real numbers, okay, the dimensional numbers of flow parameters. Okay, so here I said, okay, so here we have U, so say it's non-rotating. You're non-rotating, then we have same, very similar to this, except this N is replaced by NM. Okay, and then you got here NM here, you have NM here. Okay, so that's okay, non-dimensional parameters, but you only have two of them, independent. Okay, either these two or these two or these two. Okay, and that's your choice you want. Okay, for convenience, which one is better to use? Okay, so you can have this this whole number, but it is moist whole number. So now we call this Fm because of this. Okay, and then that can be a whole number. Okay, and so for larger whole number, represent more linear flow. Okay, and a second non-dimensional control parameter is h over a. That's a slope, steepness of the mountain slope. Okay, that's h over a, or non-dimensional mountain width. You can say non-dimensional mountain width, or you can say it's kind of measure of hydrostatic effects. Okay, the larger of this number is more hydrostatic. Okay, the smaller this number, it means more non-hydrostatic. Okay, so then you can, okay, so this H over A and NA over U measure the non-hydrostatic effects. Okay. So if NA over U much greater than 1, the flow is reaching hydrostatic, okay, approximation, balance. On the other hand, the non-hydrostatic effects cannot be ignored if this criterion is not right, not correct. Okay, you have to have NA over U greater than 1. So say if we have U equals to 10 meter per second, okay, and then we have NM is like, for example, NM normally is smaller than N. So say if say 0.0, say 5, okay, per second. And then, so say if A is 10 kilometers, then NM times A divided by U will be 0.05 times 10,000 divided by 10. Okay, so then 0.05. So this will be 500. So then it will be 50. So it's pretty hydrostatic in this case. Okay, so you got to know how to determine. Okay, sometimes in a test, okay, people may ask you, give you some numbers, okay, and don't give you any information, but give you a number NM, okay, or N, and give you A, give you U, and tell me, okay, it's non-hydrostatic or it's hydrostatic. Can I ignore non-hydrostatic effect? Can I use hydrostatic, okay, frame of reference of the equations, okay. Okay, and other problem, a problem coming out if the upstream flow is not saturated. It's just partially saturated. And it happens when you have conditional, unstable flow upstream, then that's not saturated. You cannot use NM, so you use NW. Okay, NW is also blunt vessel frequency, but it is unsaturated. Okay, so like in Chen and Lin 2005 paper, Chen, that is Dr. Suhua Chen. Okay, some of you probably know her. Okay, she comes here to visit too. Okay, sometimes in summer, last summer, I guess. And this Lin is okay. Yeah. We have Dr. Lins. Okay, Miss Lin, Mr. Lin, Dr. Lin. Okay, Professor Lin. Okay, we have Dr. Lins. Lin is a big name, right? We have number 2. We are only behind Chen. Okay, okay. Chen is number 1 in Taiwan. In Taiwan only. Okay, Lin is number 2. Okay, yeah. Đan niệm khô đi chua, thiên hạ chăm chỉ bỏ. Okay. Okay. Unsaturated blunt vessel frequency defined like this. Okay, and it's same thing except you replace theta by virtual potential temperature. Okay, and then you can estimate it. Yeah. Okay. So if flow is over a mesoscale, meso-alpha scale or larger scale mountains, okay, like in economy, my thinking is economy like U.S., China, Russia, those are kind of synaptic scale countries, okay, and like in terms of economy, okay, and like Japan is probably meso-alpha. Okay, like South Korea and Taiwan are probably meso, beta, gamma scale countries. Okay, economy. So something meso, alpha, or synaptic scale countries can do. Okay, mesoscale countries cannot do because you need probably bigger market to support your industry and have to be more complete. Okay, so you have to get focused. Okay. So then you can have Rossby number here, U over FL. Okay, normally for mountain, we replace L by A. That's Rossby number. Okay, so if somebody asks you what's U over FA in a, okay, that's Rossby number. Okay, for flow over mountains. Okay, so this one, if F is important, this have to be small. That means either F to be large or A to be large or both to be large to make it smaller number. That means your rotation effect will be larger. Okay, and then you have NH over FA. That's called the Berger number. Okay, it's a natural choice of additional non-dimensional number. Okay, now the moist flow regimes. Okay, so say let's look at the simple one, 2-dimensional flow regimes. And here I have let me see. I don't know, when I copy, I couldn't get it here. Okay, I couldn't get it here. So what should I do? Yeah, I don't know why. Sometimes I don't know. They keep changing things. Okay, software they keep changing. Even words. Okay, word they keep changing. So before I was able to do it, I don't have to worry about it. But now I have to use a special form to stick with it. Okay. So here, what should I do? Okay, let's do this. It's good thing is I have my own website. Okay, so let's do this. Let's look at Chu and Lin's paper. That's in 2000. Chu is he was my former student from Taiwan. Okay, he graduated from Zhongzheng Ligong Xue Yuan. Okay, so Oh, see here you have see the filter mechanism here. Okay, okay. So here, okay, we use idealized sounding. Okay, and to do it, and we have certain cap. This was proposed by Weissman and Klemp in 1982 paper. Okay, so now we have three regimes. Okay, one is when U over NH, here we use NW. Okay, unsaturated, because for conditional unstable flow, it's not saturated. If saturated, you cannot have cap. Okay, you cannot have cap. You cannot have cap. Okay, if saturated, it's moist and neutral, you cannot have cap. Okay, you cannot have, because you need to be able to get the to LCL, okay, and still stable, and you have to force it up to LFC, and then start to become unstable. That's why it's called conditional instability, because you need to force it. Okay, it's dry, partially moist, but not not the kind of saturated. So then when the flow number is small, then what happens is, okay, the kinetic energy associated with the basic flow coming in, incoming flow, is weak, and then the cloud produce rainfall, have evaporation that produce density current that is able to push against the basic flow. So flow coming in weak, and then this density current can push against it. Okay, and then one by one formed. But then once you formed, we migrate and develop, okay, in the wind direction. But one by one, so the whole system, individual cloud develop and then migrate to the downstream side. However, the whole system is migrate to the against flow to the upstream. So basically, what we have here is, okay, so say here is mountain, okay, and then once your flow comes in, okay, we have U, where NW comes in, okay, and this mountain height. So when U over NH M, NW H is small, low flow number flow, then you form the okay, thunderstorm, score line, and then you got precipitation, and then you develop density current, and then the push, and then push, you got, okay, a kind of conveyor shell develop, just like super shell, just like a multi-shell storm, okay, and then you push, and then this will migrate vector downstream and develop, okay, and then other one form like this, okay, so this will go to the, okay, and then other form, okay, go like this, because this one is strong, the, okay, density current is strong, okay, and but the whole system is developed, okay, migrate to the upstream against the flow, but individual one keep developing and migrate, okay, moving toward east. So then you have the system, see individual one develop, migrate to the downstream, okay, and then other, this is this one regime, okay, regime one, and regime two is when you have U increased, then density current, they are in balance, so then the system will be developing on the upslope side, and that can produce heavy rainfall, okay, and then you keep increasing the whole number, then it's going to, okay, whole system, because wind is so strong, so once you develop, you go like this, and then your density current cannot have enough forcing, okay, against the basic flow, okay, so then the whole system, and you still have the stationary, okay, rainfall over the mountain, but the conveyor system okay, kind of migrate, okay, propagate to the downstream side. So you have 3 regimes. Okay, so this is what the cloud, the mission figure is like this. I don't know why it's missing. I didn't have problem before, but just in recent months I have this problem. Okay, so that is, you have high full number flow. Okay, so then you have this question here. I let you read it. Okay. Okay, so if upstream propagating conveyor system, that's regime 1 on top 1. Okay, this one. Okay, and then regime 2, this U is stronger, so you got stronger, larger kinetic energy associated with the basic wind, and this density current are in balance with it. So the conveyor system will develop and become stationary over the upslope. Okay, and that is stationary conveyor system. And then if U become larger or full number become much larger, then both stationary conveyor system over the mountain develop, and also the stronger one will migrate, propagate downstream. Okay, so these are found by, I have another mission too. Okay, oh, this is the one I talk about after Chu and Lin. Okay, 2000. And then I think I have another mission, I believe. Okay. Yeah, so. Okay, oh, I'm lucky. Okay, we are lucky. We have this one. Okay, then this one was published by Suwa Chen and me. Okay, Chen and Lin. Okay, so we have this. Okay, so we add other complication. Beside full number, we also add the cap. We change the cap. In the Chu and Lin, we have the cap fixed, but here we have different caps. So we have 4 regimes. Okay, so then you have one, okay, which this forcing by density current is larger than the basic flow. Okay, so it can migrate upstream. And then you have regime 2. These 2 are in balance. So you have a conveyor system developed over the mountain. And then this is out of the many simulations using the WRF. And then regime 3, okay, then you have this conveyor system developed here, and then this one keep developing because wind is stronger. So see here, this kinetic energy associated with basic flow is larger than forcing by the density current, so you migrate downstream. And then when it becomes very large, then this becomes kind of stratiform cloud, and then the conveyor cloud propagate downstream. Okay, so we have these 4 regimes, and then they based on the full number and the cap, because then you have large, small, so you have 4 cases, 4 regimes. And then you can have 3-dimensional flow regime too. Okay, I probably let you read this. Okay, and Dotono also, his colleagues also pursuing this research. Okay, but we started earlier. Okay, in 2000 for kind of conditional unstable flow. And let me, okay, this appendix I let you read it. Okay, the conditional instability. Okay, the difference of conditional instability and potential instability. Potential instability is also called convective instability. Okay, and there are different kind of instability. The conditional instability is very important. The conditional instability is, you look at air parcel, you go up, okay, and then you pass LCL, you have to keep forcing because they are still stable, and then until you push, okay, higher than LFC, the level of free convection, then the air parcel will become warmer than the environment, and then just go crazy, and that's conditional instability. But potential instability or convective instability is different. You're talking about their instability. Okay. So when you lift the air, I think probably most people understand very well of the conditional instability, but not conditional instability, not potential instability here. So you're interested, I encourage you to read this because it's very important concept. A lot of people are not very clear. Okay, I tell you. See, it's like here you have a there. You have a there, A to B, and then B is drier, very dry. So then when you lift the whole layer up, okay, like you have a layer of fluid, you come here over the mountain, and then whole layer being lifted. Then this can happen, okay. And so then upper one will follow dry adipate, become B prime. And A, because it's conditional, unconditional, okay, conditional unstable flow, so it's going to go with dry adipate and then become saturated at LCL and then keep going, okay, and then pass this LFC and then keep going to A prime here. So you lift same height, B, okay, to B prime, A to A prime, and then become unstable. Okay, this is called potential instability. Okay, different. Okay, so I'm going to test you guys this. Okay, it's very important. Okay, so I taught you a problem already. Okay, yeah. So this great. Okay, and of course there are a lot more to be learned. Okay, this is just providing the basics. But if you can start, you can keep reading, keep thinking. Even you don't. Okay, it's only in one summer. Okay, but you have lecture notes, you have books. Okay, your book is not enough. Okay, sometimes the book is not enough because the book is good summary of what had been done before, but it takes a while to publish a book. Like it took me six years to publish a book. Okay, so there are some new development that you will be relying on the literature, the research papers. Okay, so just keep reading, keep thinking, then you should have the background, okay, to do that. Okay, yeah. And then let's take a break, and then next hour, you tell me what you like to be in that test. Okay. Okay.